Before we proceed to the enthalpy of solution, allow me to start by discussing the enthalpy of formation. Now, first, what is enthalpy of formation? Now, if I talk about the enthalpy of formation of, say, carbon 4 oxide, there are so many reactions that can lead to the formation of carbon 4 oxide. I can react carbon with oxygen to give me carbon 4 oxide. I can react carbon 2 oxide with oxygen to form carbon 4 oxide. I can even burn methane and the other hydrocarbons to give me carbon 4 oxide. So I want to give a definition that is going to exclude all other and leave me with only one of that of those equations to be the enthalpy of formation. Remember, when I talk about the enthalpy of formation, I'm not talking about the enthalpy of precipitation. Okay, I'm not talking about the enthalpy of preparation. I'm talking of the formation of a substance. So we restrict ourselves to a reaction that involves elements. So I will define enthalpy of formation as the amount of energy that is either produced or absorbed. So you can simply say the energy change when 1 mole of a compound is formed from its constituent elements. The word constituent again, but I don't have to include that word as long as I'm saying that the substance must be formed from elements. So when I look at these reactions, the first reaction, the reaction between carbon and oxygen to form carbon 4 oxide becomes the enthalpy of formation of carbon 4 oxide. Why? I am getting the carbon 4 oxide from the element carbon and oxygen. Now, when you look at this one, it's okay, I'm getting carbon 4 oxide, but is it being obtained from the element? And the answer is no, because an element is a substance that cannot be spread into any simpler substance by any chemical means. And that is what we said in Form 1. So carbon 2 oxide can be spread to carbon and oxygen, and therefore this is not the enthalpy of formation of carbon 4 oxide. Why? Because it's not being formed from elements. So in fact, if I want to get the enthalpy of formation of anything, now what I need to do, like if I want to get the enthalpy of formation of sodium carbonate, I'll just write the sodium carbonate and then split it up to elements. So what are the elements in sodium carbonate? I have sodium, that is in solid state, plus carbon, plus 3 oxygen. So 3 over 2 O2. That, the enthalpy of that reaction shall be the enthalpy of formation of sodium carbonate. So of course, because we are supposed to be talking about the standard state, then you now add the standard state after whatever that I've said. So this becomes our working definition. The enthalpy of formation is the energy evolved or absorbed, or you can simply say the energy change when 1 mole of a substance is formed from the constituent element at the standard state. That is the enthalpy of formation of a substance. So remember, the most important thing in that definition is that the compound must be formed from elements, and not from any compound. So we have an example there. I want to give the equation for the formation of ethanol. So I've just said I just need to write the ethanol and work backward. What does it consist of? 2 carbons, and they should be in the standard state. The standard state, the most stable state of carbon is graphite. So I'll talk about the carbon in form of graphite. Then how many hydrogen? These are 6 hydrogens, and then there's only 1 oxygen. So plus I have oxygen. Now you could try and write the equation for the formation of calcium carbonate. You have a second for that. And then write the equation for the formation of methanoic acid. So, but remember, at the end of the day, the substance must be formed from constituent elements. Now, you realize therefore that some of these reactions are next to impossible. Like the one I've just indicated there. This is what we call direct synthesis in form 2, when we are preparing salt, by the direct combination of elements. But you cannot compare, the only salt that you can prepare by direct synthesis are binary. They must be binary. A salt that contains only 2 elements. Otherwise, you have more than 2 elements, that reaction is impossible. So this is an impossible reaction. You cannot combine carbon, hydrogen, and oxygen to form ethanol. That reaction will not take place in the lab. So how do you get the enthalpy of this reaction? Now, the enthalpies of most of the reactions will be determined indirectly by using what we refer to as the Hess law, or the law of constant heat summation. According to the Hess law, the Hess law states that the enthalpy of a reaction is independent of the path taken. So if I'm starting from a substance A and I'm getting to a substance B, it doesn't matter how I get there. I can start from A, get to C, get to D, and then eventually to B. So the enthalpy of this reaction will be the same as the enthalpy of the other reaction. And this is, of course, a consequence of the law of constant heat summation. You are not likely to get more energy because you have followed a different route. Because if you do that, then you have created some enthalpy, some energy has been created in the process. If you get more energy during this than during the other, then you have lost some energy when you took the alternative route. When you took the alternative route, you have destroyed some energy. So, because that is not possible, then the enthalpy for this process must be the same as the enthalpy for the alternative process. Now, what we shall do is we shall carry out a virtual experiment, sort of, to verify, to demonstrate the Hess law. So, in this experiment, I want to find out if I reacted sodium with hydrochloric acid, the solid sodium and hydrochloric acid. So, not solid, so that would be explosive. Let me use sodium hydroxide in solid state. I react it with aqueous sodium hydroxide. That, of course, will give me sodium chloride and water. Yeah, that is true. That is what I get. And that is going to be in aqueous state, and that is also going to be in aqueous state. So I can react that directly. Sodium can be reacted directly with, or sodium hydroxide can be reacted directly with water to give me sodium chloride. Now, the alternative way of doing that is maybe to dissolve the sodium hydroxide. Can I dissolve the sodium hydroxide in water? So let me add plus water there to give me aqueous sodium hydroxide. Now, I've not done anything to the hydrochloric acid. Then I react that. Now, what am I saying? That it's possible to react sodium hydroxide with an acid in using 2 ways. I can either react it directly with the solid sodium hydroxide with hydrochloric acid to give me the sodium chloride. Alternatively, I can dissolve the sodium hydroxide in water and then react it with hydrochloric acid. From the Hess law, what do you think from the Hess law? You can take some time, talk to somebody, pause the video. Now, but I hope this is what you are saying, that the direct should be equal to the alternative. So it doesn't matter how I react the sodium hydroxide with the hydrochloric acid. If I reacted it directly, I'll get the same energy as when I dissolve it first and then I react. So that is what I want us to verify by means of an example of a virtual experiment. In the first experiment, we will react the sodium, we will dissolve the sodium hydroxide, and then we shall determine the enthalpy of solution of sodium hydroxide. So as you observe the first script, please extract this data: the mass of sodium hydroxide, extract that, the volume of water, the initial temperature, and the final temperature. Note that the apparatus that are being used in this setup are another level. I hope one day we will get there. If we are not there already, where you extract, you just put the probe in the solution, and it plots its own data. You just read from the graph. That's rather that's nice. So, but do copy that. Then after you have done the first experiment, work out the enthalpy of solution of sodium hydroxide. You can pause once you have done the experiment. So look at the script and extract that data.
I have 2 grams of solid sodium hydroxide. Go. So for the first reaction, we're going to add 100 milliliters of distilled water to the styrofoam cup. And suspend the temperature probe into the solution so that you can measure the initial temperature. And then we're going to add the 2 grams of solid sodium hydroxide.
I think the reaction is done. And then now we're gonna just measure.
And we're gonna stir continuously
making the gas pressure
for about 200 seconds.
And we are gonna do this by making the water
You see the graph?
inside
Look at
the
the
tube to equal to the water.
As you can see, all of the solid sodium hydroxide has been dissolved, but we're going to keep stirring until the maximum temperature has been reached. The temperature doesn't look like it will be changing much, so we can stop the data collection here. So that's our first reaction.
Assuming that you have gone through the script now and you have that data, please calculate the enthalpy of solution of sodium hydroxide. Assuming that you have done that, let's look at what I did. Now this is the data I got. I got the mass of sodium hydroxide. Mass of sodium hydroxide that is being dissolved as 2 grams. So enthalpy of solution of sodium hydroxide. Mass of sodium hydroxide is 2 grams. The volume of water is 100. I hope that's what you had. Now when I look at the graph, it is of course towards the end there's a summary. So the 24.9 to 30.24. Note that with the ordinary thermometer you can only get to 0.0, 30.0 or 30.5. Now so I got that as my delta T. So what is the heat change? MC delta T. Now we may not have discussed the enthalpy of solution, but remember what we said when we were talking about displacement, that you ignore any solid. Ignore any solid. So we are going to ignore the sodium hydroxide. we're only going to use M as a value of water. So whatever that is surrounding the thermometer is the water, the 100 cubic centimeters of water whose mass convert to 100. So times all that MC delta T, and that is the amount of energy I got from that. So the moles of sodium, of course, are 2 over 40. Yeah, the mass of these are moles of sodium hydroxide. So the mass of the relative formula mass, which comes to 0.05. So the 0.05 is what is producing the amount of energy. So what about 1 mole? So that is what I get, negative 44.69. That is the dissolving of the sodium hydroxide. Now the next experiment, we will get the enthalpy of a reaction between sodium hydroxide solid state and dilute hydrochloric acid. So just observe the creep. Observe the creep and extract the data for the reactant solid sodium hydroxide and dilute hydrochloric acid. Get the mass of sodium hydroxide. Get the volume of 0.5 molar hydrochloric acid in the process. Get the initial temperature and the final temperature. Then get the delta T. Then get the enthalpy of a reaction per mole of sodium hydroxide. So you can observe that creep.
So for the second reaction, we're going to add 100 milliliters of 0.5 molar hydrochloric acid to the styrofoam cup. Then we're going to collect the initial temperature. And we're going to add approximately 2 grams of solid sodium hydroxide. Then we're going to start stirring this. So you can see this, again, it's an exothermic reaction, and the temperature is rising.
And use it to determine the enthalpy per mole of sodium hydroxide. Now this is what I forgot. The temperature change of they are using 100 cubic centimeters of 0.5 molar HCl, 2 grams of sodium hydroxide, not sodium. Then the temperature, the initial temperature 25.61 and the final temperature 37.53. So delta T comes to 11.92. So MC delta T, I am again ignoring sodium hydroxide. It is in solid state. So ignore any sorry. So ignore it 100 times that. That is the amount of energy. The moles of sodium hydroxide again 0.05. So the amount of energy that is produced by that reaction, I hope you are getting to around 100.128. Depending on the C that you used. I'm using 4.2 joules per gram per Kelvin. You could have used 4.17 or 4.18. That the answer is going to be slightly different. As long as you use the same for the 3. Now finally, what do I want to do? Now get the enthalpy of the reaction between dilute sodium hydroxide and dilute sodium hydroxide and dilute hydrochloric acid. Again, you can go through the final part of the creep, extract the data. Volume of 1 molar sodium hydroxide used, you can write it down there. Volume of 1 molar hydrochloric acid used, write it down. Get the initial temperature and the final temperature. That is from observing the creep. So as you observe the creep, just extract that. Now
So this is our third reaction, and we're going to put 50 milliliters of 1 molar hydrochloric acid into the styrofoam cup. And we're going to measure the initial temperature and record it. Then we're going to add 50 milliliters of 1 molar sodium hydroxide to the cup. And we're going to stir.
You note that the reaction between sodium hydroxide and hydrochloric acid solution is almost instantaneous. Look at the shape of that graph. As you do that, look at the shape of that graph. It is immediately the two are mixed. The graph looks like this. Well, the others were it was taking quite some time. It was taking quite some time, but this reaction is almost instantaneous. Now, can you explain that in terms of the cohesion theory? Yeah, we said according to the cohesion theory that when the substance is dissolved, the reaction has a maximum rate. Why? Because the particles accelerate each other. They accelerate each other, so they collide. The collisions are very energetic. They are the negative and the positive. The positive hydrogen ions, the negative OH ions, as they approach each other, they accelerate each other. So when they collide with a lot of energy. So then definitely a reaction is going to take place. But when you have a solid, it's only the particles on the surface that are actually reacting. So it takes more time. But that is another topic altogether. So let's proceed now. Assuming that is done, you have extracted the data. Please go on to calculate the enthalpy of that reaction between the sodium hydroxide solid and the dilute hydrochloric acid. And that is what I have. So that is the data, 50 grams of the sodium hydroxide, 50 grams of the hydrochloric acid, the initial temperature and the final temperature. So temperature change 6.28 degrees Celsius. So what about therefore the amount of energy produced? I got that much, 2637.7 joules. So that is for this number of moles, that's 0.05. So 1 mole will give me negative 52.75 kilojoules. And let us now apply the Hess law. Now, from the Hess law, where we started from, we said there are two ways of reacting sodium hydroxide and hydrochloric acid. Number one, you can first dissolve it in water. You can first dissolve it, then react. And that's what I have represented here. The sodium hydroxide dissolved in water. That is it. This is the first reaction. That is 44.688. That is what I calculated it to. Then react the solution with the hydrochloric acid. That is the last reaction. The sodium hydroxide solution with hydrochloric acid. That is for the last reaction. So that was 52.752. Now the other way of doing the reaction is to react it directly without dissolving. Just react the sodium hydroxide with hydrochloric acid. So I got 100.128 kilojoules. And so that is it. So what is the relationship? This plus that should be equal to that. So it doesn't matter whether I do it this way or do it this way, the energy should be the same. And this is what I have. So I have worked it out to 97.44. The other one is of course 100.128. What do you think? Now, if were it not for experimental errors, the fact that the container may be absorbing some energy, I did not even, I did not cover, so there must be some convention. There must be some energy change, some energy lost, and that should be what is, that can account for the small difference of around 0.3 or 3 kilojoules. That small difference could be due to energy. So actually this shows that the Hess law is correct. So what we normally do when we use the Hess law to work out maybe the enthalpies of some reactions is we connect reaction. We connect reactions by what we shall refer to as an energy cycle. We draw an energy cycle by linking up. Yeah? We link up reactions. We are given some thermochemical equations. We link them up, and by so doing we can get the enthalpy of an unknown. Let's do that by means of an example. And I'm given here, calculate the enthalpy of a reaction, carbon plus hydrogen to form ethine. I don't know the enthalpy of that reaction, but I'm given some enthalpies here. So what we normally do is try to get a reaction that is as richest as possible. It has most of the elements. Now we cannot choose this, we don't choose this. We can choose this, the required one, but I choose to use this, although I could have chosen that. So let me write it down. C2H2 plus 5/2O2 to form 2CO2 plus H2O. I've just written down that equation. That's negative 1299 kilojoules. It is the best. It has, it may be lacking carbon and oxygen, but it has many other elements, many other of those substances. Now, so this is the reaction I've used. Let me remove it. So this, let me try to link these here. Now I already have the ethine, but I don't have carbon and hydrogen. I'll have to put them somewhere. I put them. Why? Why do I put them there? Because it's supposed to be a cycle. It's supposed to be it's sort of a triangle. This is the way the cycles look like. There are initial substances, there are intermediate substances, and there are final substances. That is how it's going to look like. Initial substance, so from an initial to intermediate or stopover. Then to the last thing, also all from the initial to the final. So there are three stages in an energy cycle. The starting point, the stopover, and the end. That is how it's going to look like. So you can start from the initial to the stopover to the final, or you can start from the initial to the final. So there will be three stations. Let me call them that for lack of a better term. So there will be three stations, a station, two, and a third one. Now I have the first and the second. I just need to put the third station. Now, so what do now back to what I was doing. I want to connect this. Now I already have that, but I don't have carbon and hydrogen. So I need to write them down. 2 carbon and 1 hydrogen. So the arrow is in that direction. Why is it in that direction? Because it is this reaction that I've written there. It is this reaction that I've transferred to link it up. So how does the reaction look like? 2 carbon plus a hydrogen to form ethine. So it is in that, the direction is crucial. You change the direction, you get everything wrong. So that is, and this is what is required. That is the enthalpy of a reaction that I need. So I've already dealt with that. So I get to this one. Carbon plus oxygen. Do I have carbon? Yes, it is here. Do I have oxygen? I can write some oxygen there to form what? carbon 4 oxygen, because the carbon 4 oxygen is already there. It's already there. I'm not adding anything because everything has already been met elsewhere. So I just use them the way they are. So the carbon is already there. The oxygen is already there. All I need is an arrow. All I need is an arrow to form 2 carbon 4 oxide. Now note that this reaction, this is the molar enthalpy of combustion of carbon. So for 1 mole of carbon. But look, I have 2 moles of carbon. So this is going to be 2 times negative 393.5. 2 times that. That is what it's going to be. It has to be. Because this, whatever I have is for 1 mole. Now, the other one, what else do I have? Now this is taken care of. Now I need this. Hydrogen and water. I already have hydrogen, I already have water. All I need is an arrow. All I need is an arrow. So, and then this is 1 mole of that, and that's 1 mole of that. So I don't need to multiply by anything. 285.8. Now I can balance the oxygen. How many oxygen will be required here for this to happen? I can bet there's going to be 5/2. Yeah, just count. These are 4 plus 1. These are 5. This, all the equations balance this way, balance all directions. So that is the energy cycle. That is something that you need to practice doing. Can we do that again? Allow me to take this as my reference. I hope that is not abuse of terms. C2H2. Now allow me to use that as my base equation. Now get to this. Ethane plus 5/2 oxygen. I already have the ethane, so what do I need? To add 5/2 O2, and that will give me CO2 plus H2O. I need to balance that. I need 2 of that, 2 of that, but 1 of that will do. But these are already 5/2 oxygen. Have I done it with that equation? I think so. Then what else? Now carbon plus oxygen. Now I already have carbon here, so which I need to add oxygen. I have seen some people put it on the arrow. It's still possible. So I can just, I already have carbon 4 oxygen. All I need is some oxygen. So I can put that in that direction. So this is this reaction. Carbon plus oxygen to form carbon 4 oxygen. Now again, the last, I can put the energy there, but we need to multiply that by 2. The last one, 2 hydrogen plus oxygen to form water. I already have the hydrogen, I already have the water. All I need is an arrow. Then I need to ensure that I have the right number of oxygen, which is going to be simply 5/2. Again, I said you can write them on the arrow. So that becomes my cycle again. So you can start with this or this reaction. But starting with these two, they contains too few elements. So I have already drawn that cycle. Cycle looks like that. Now where are we starting from? So that we can apply the Hess law. Where are we starting from? Now to know where you are starting from, look at the arrows. Where you start from, arrows only get from there. That is a source. That is a source. That is a source. We don't have an arrow going into that. We don't have any arrow going. That is the starting point. If there is anything, if there is an arrow, it must be coming from there, not getting inside there. So this is the start. That is the start. Now, what is this? This is a stopover. Why? Because things are getting in and getting out. Getting in and getting out. So this is a stopover. The intermediate. And this is of course the final. Hakuna kitu inatoka hapo. That is Greek. Nothing is coming out of there. Everything gets there and that's the air. Nobody is getting out of that place. That is, we say they have arrived. Nobody's getting out of there. So the start, the intermediate, then the end. So what is the relationship from the Hell's law? Now from the beginning to the end must be equal to from the beginning to the stopover to the end. From the beginning to the end is the same as from the beginning to the stopover to the end. So from here to here is the same as from here to here, then to there. And that is what I've represented here. Now the delta H, that is unknown, plus negative 1299.5 is equal to the alternative root. This plus that plus that. So that is what I got. That is this. The rest is arithmetics, not even mathematics, by the way. That is arithmetics. So my enthalpy is coming to positive 226.7 kilojoules per mole. I think we can do with another example. So calculate the enthalpy of the following chemical reaction: the carbon disulfide or carbon 4 sulfide plus oxygen to form carbon 4 oxide and sulfur 4 oxide, and that is what we are given. So what did we say? Choose any and then read the other reactions around it. I have chosen that because I don't want to choose this and that are weird. You can also choose this, but this and that, please don't. So I have carbon disulfide plus 3O2 to form CO2 plus 2SO2. So this is a reaction, and it's the one I don't know. Now let me get to this. I already what do I have? I don't have any carbon there. I have carbon 4 oxide, and the arrow is I don't have carbon and some bit of oxygen. Now I'll put the oxygen towards there because I'll need them somewhere. So let me draw that. So carbon, to form carbon 4 oxide, I need only one carbon 4 oxide. So only one carbon will be required for that. Now, so this is the reaction I've already ringed. That is negative 393.5 kilojoules per mole. Now I go to the next equation, sulfur plus oxygen. Do I have sulfur? But I have sulfur 4 oxide. So I need to add sulfur and then put an arrow. I need to add sulfur and put an arrow. But I need 2 sulfur 4 oxide. So that means I need 2 sulfurs. I need 2 sulfurs. So for this reaction, how many oxygens are required? How many oxygens are required? I have these are 4 plus 2, 6. So I need a 3 there. I need a 3 there. Now, so that is done. But what is the enthalpy of this? Negative 296.8. Good. Times 2. Times 2. Yes, you are thinking. Times 2 quantity, because this is the enthalpy per mole of sulfur 4 oxide. But I have 2 moles of sulfur 4 oxide, so I need to multiply that by 2. Now then get to the last equation, carbon plus 2 sulfur to form carbon disulfide. Do I have carbon? Yes. Do I have sulfur? Yes. Do I have carbon disulfide? Yes. So what do I need? Simply an arrow. All I need is an arrow in that direction, and that shall be it. Now this is positive 87.9. That is the energy level. That is the energy cycle. Now, what do you think is the relationship? Okay, where am I starting from? Look at the arrows. They are all coming from there. So this is my starting point. Now, what is this? My stopover. It's my stopover. Why? Getting in, getting out. And this is my end. What is the relationship therefore? From the beginning to the end is the same as from the beginning to the stopover to the end. That is the energy cycle. So I have done it again in a. So that is the energy cycle that I got. I hope we still have the same. Okay, but this energy cycle lacks oxygen, so 3/3 oxygen can be put. It is good to always balance them. So the start to the end is the same as the start from there to that. So this plus that, those two is the same as start plus the delta H that is unknown. So my delta H has come to 1075 kilojoules per mole. Yeah, that is, I think it's easy. You can practice with the drawing of energy cycles. I have a question for last. Construct a Hess law cycle and energy cycle to calculate the standard enthalpy change for this reaction: carbon in form of graphite to form hydrogen, and hydrogen to form ethanoic acid, given the enthalpies of combustion. So they have not been written, but we can write the equations. I know we can write equations. The enthalpy of combustion of carbon, that is carbon plus oxygen to form carbon 4 oxygen. The enthalpy of hydrogen, hydrogen plus a half oxygen to form then ethanoic acid plus, so combustion. So we can then choose this and come up with a cycle. Please, you can pause the video as long as you wish. Work out and then see if you are going to get 484 kilojoules. See if you get 484 kilojoules. Another example that you can also attempt, copy the example, see if you get to 390.3 kilojoules. Please make sure that you attempt the question. Pause and attempt. You can discuss it with a neighbor, your teacher. Yeah, it's a route to consult. It's not an exam. And our last example is right there. Attempt it and see if you can get to that answer. If you can do the three, they are interesting questions. So when you get to the KCSE type of questions, they will be walkover, because these questions are a bit interesting. They're not difficult, I said, they are just interesting. Now, having done that, therefore, we will get back to the enthalpies of solution.